Hi, I'm Eddie. I'm from grade 6. So today I'm going to talk about how do I actually design my major equipment, which is the C501, the methanol distillation column. Without further ado, let us proceed with the introduction of the distillation column. So basically here I'm going to help you understand how does the C501 works. So here I present you the distillation column with the tag number of C501. So basically the flow of here inlet feed will be around 268,000 kg per hour with a composition of methanol 93 weight percent, water 6% and CO2 of 1%. So the purpose of the distillation column is basically to purify this methanol by separating out the water. So from this bottom of this column, it is basically consists of the water, and of this overhead of the distillation column, it mainly consists of the pure methanol with the purity of 98%, water and CO2 1% each. This presentation is continued with the major equipment C501 design. So basically here I'm going to present you the design methodology, basis selections, and a little bit about the sample calculation. So basically, this is the design methodology that I have. I start off with a process design for which the diameter and the height of the collar will be estimated, and the number of feed stages, and then where does the inlet of the feed, it's going to feed at which stage, and then there's operating pressure, temperature, and it's going to be followed by the mechanical design. And then I'm going to show you the technical drawing and also the specification sheet, and then there is the SOP and also the cost evaluation. But in this presentation, I'm just going to stop until here the specification sheet and the technical drawing. Before we proceed with the column sizing, we have to determine what is a suitable tray that can be used in our distillation column. So basically, there are three types of tray commonly. One, bubble cap tray, sieve tray, and also the valve tray. All of these three trays, they have their own pros and cons, which we will further explore. So eventually, it is determined that sieve tray is the best among the three trays. Firstly, let us see in terms of the cost. In terms of the cost, it is the cheapest compared to the bubble cap and also the valve tray. In terms of the capacity, it has the minimum capacity of 70%. Then, if let's say we go for the valve tray, it's only 60%. Then, in terms of the bubble cap tray, it is only suitable for those operations with a lower vapor and also the liquid flow. In terms of the efficiency, all of these three, they are efficient, so there's no real distinction. And finally, we will see the pressure drop, for which the sieve tray, it experienced the lowest pressure drop as it is not restricted by the caps. So it is determined that sieve tray is the suitable tray for this operation. And following next, I'm going to proceed with how do I actually determine the number of stages. So before that, I have collected the operating condition for which the temperature I have extracted for icon simulation is around 36.32 degrees Celsius with a pressure of 2 bar. It is followed by the determinations of the vapor pressure by using the Anton equation, and this is a summary of the result that I've calculated for the methanol and also the water. And it's followed by the relative volatility of the methanol to water, and eventually I calculated the minimum reflux ratio by using the Underwood equation, and it is determined that the minimum reflux ratio is approximately 0.258. After calculating the minimum reflux ratio, I have to determine what is the actual reflux ratio that is needed by this operation. So it's just be done by multiplying 1.5 with the minimum reflux ratio, and it is determined that the actual reflux ratio is around 0.387. And next, I'm going to plot the mercaptan curve to determine the number of stages. So basically, this is a general view of the mercaptan curve. So these are the steps to plot this graph, for which I have the equilibrium curve, the 45-degree line, and at the bottom, feed and also the distillate compositions, and there will be the Q line, and I'm going to draw the operating line for the rectifying and also the stripping section. So basically here it shows the outcome of our mercaptan curve based on our operation, and from this mercaptan curve, it is determined that the number of stages is around 12 and then the feed tray is at 2. So by incorporating the O'Connor correlation efficiency, which is calculated to be 48%, it is determined that the actual number of stages, which is determined by dividing the 12 by 0.48, is 25. And with the Kilbride equation, the actual feed tray is 13. So in summary, the rectifying section will be 12 plates and the stripping section around 13 plates. Next, let us see the height estimation of the column. So this is basically the diagram of the column. And then before calculating the height, we have to make some assumptions, for which the first one, the plate spacing between the tray edge should be around 0.45 meter, which is according to the Petronas technical standard. And the additional space will be around 15%. So by using this column height estimation formula, it is determined that the total height excluding the top and the bottom closure will be approximately 12.94 meter, and then the total height which included the top and bottom closure will be 14.81 meter. So what exactly is this top and bottom closure? So for this top and bottom closure, here, this and this is the top and bottom closure. So it's determined that the torus spherical head is being selected. So the torus spherical head, by zooming in, it looks like this, and these are the specifications, or these are the components that's inside this torus spherical head, which is important for this to calculate the overall height of the head. Let us proceed to the column diameter estimation. So to estimate this column diameter, there are a few formulas that we have to follow through. So first, let's determine what is the liquid vapor factor, the correction factor, the flooding velocity, and eventually I determine what is the inner diameter of the column. So moving on next, so let us zoom into what's happening inside the column. So let us see the column internal. So basically this is how the column internal looks like, where I have the downcomer area with the area of 1.22 meters square, and then the rear length of 2.7 meters square, the tray spacing like I've just mentioned according to PS 0.45 meter, active area 7.74 meters square, tray hole diameter around 0.005 meter, and then I determine that my area of one hole will be 1.96 to the 10 power of -5, and then the number of holes will be approximately 86.7 thousand. Next, let us proceed with the nozzle calculation. So for this nozzle, we are looking to the feet, the top, and also the bottom nozzle. So here are the material specification for the nozzle, for which the design pressure around 2.2 bar, corrosion allowance 2 mm, the welding efficiency 0.85, and eventually it is calculated that the feed nozzle will have the diameter of around 0.94 meter, the bottom which is 0.44 meter, and also the top nozzle will be around 0.9 meter. So here I'm going to show you how the technical drawing is being presented and the specification sheet. Here I present you my technical drawing. This is the front view of the distillation column. Here is the hydrodynamic dimension with the tray laid out and also the holes laid out, for which the pitch is being presented, and also the diameter of this hole is being specified as well. Eventually reaches the specification sheet. So basically for this specification sheet, it is the summary of all of the data that I have calculated, for which we can see that there will be nozzle, there will be gaskets, there will be bolts, the shaft thickness, the flange, and everything that is related to our process, and it's summarized in this specification sheet. So that's all for the design for the distillation column of C501. Here are the references that I referred to. With this, I end my presentation today. Thank you.